Hello students, this is Jennifer Saldana. Today we will discuss about the last part of module 3. Okay, so this is named as module 3 part 10. Okay, to start with we have the external communication interface, that is ZigBee. Okay, we discussed about so many external communication interfaces in the last video lecture. So today we will discuss about ZigBee to start with. It's a low power, low cost wireless network communication protocol based on the IEEE 802.15.4 2006 standard. ZigBee is targeted for low power, low data rate and secure applications for wireless personal area networking, that is WPAN. The ZigBee specifications support a robust mesh network containing multiple nodes. This networking strategy makes the network reliable by permitting messages to travel through a number of different paths to get from one node to another. ZigBee operates worldwide at the licensed bands of radio spectrum, mainly at 2.4 to 2.484 GHz, and also 902 to 928 MHz and 868 to 868.6 MHz. ZigBee supports an operating distance up to 100 meters and a data rate of 20 to 250 kilobits per second. ZigBee is primarily targeting application areas like home and industrial automation, energy management, home control security, medical, patient tracking, logistic, asset tracking, and sensor networks and active RFID. Automatic meter reading, smoke and detectors, wireless telemetry, HVAC, that is heating, ventilating and air conditioning applications and control, heating control, lighting controls, environmental controls, etc. are examples for applications which can make use of ZigBee technology. So, in ZigBee terminology, each ZigBee device falls under any one of the following ZigBee device category. A ZigBee device can be ZigBee coordinator ZC, or it can be ZigBee router ZR, or it can be ZigBee end device ZED. Now, what are the functions of each one of these? ZigBee coordinator ZC is also called as network coordinator. The ZigBee coordinator acts as the root of the ZigBee network. The ZigBee coordinator is responsible for initiating the ZigBee network, and it has the capability to store information about the network. ZigBee router ZR, or it is also called as full function device FFD. It is responsible for passing information from device to another device or to another ZR, ZigBee router. ZigBee end device ZED, or it is also called as reduced function device RFD. It is an end device containing ZigBee functionality for data communication. It can talk only with ZigBee router ZR or ZigBee coordinator ZC, and doesn't have the capability to act as a mediator for transferring data from one device to another. So in the figure you can see in the middle you have the nodes or the devices such as ZigBee coordinator ZC, ZigBee router ZR, and the end devices. Most of the end devices are ZigBee end devices ZED. Okay. The next external communication interface of an embedded system is GPRS, General Packet Radio Service, a communication technique for transferring data over mobile communication network like GSM. Okay, this is very similar to GSM, which requires a mobile communication network for transferring the data. Data is sent as packets. The transmitting device splits the data into several related packets, At the receiving end, the data is reconstructed by combining the received data packets. GPRS supports a theoretical maximum transfer rate of 171.2 kilobits per second. In GPRS communication, the radio channel is concurrently shared between several users instead of dedicating a radio channel to a cell phone user. The GPRS communication divides the channel into 8 time slots and transmits data over the available channel. GPRS supports Internet Protocol IP, Point-to-Point Protocol PPE, and X.25 protocol. X.25 means packet switched data communication in wide area network for communication. GPRS is mainly used by mobile enabled embedded devices for data communication. The device should support the necessary GPRS hardware like GPRS modem and GPRS radio. GPRS is an old technology and it is being replaced by new generation data communication techniques like EDGE. EDGE stands for Enhanced Data Rates for GSM Evolution. Then high speed downlink packet access, HSDPA, etc., which offers higher bandwidth for communication. The next topic is embedded firmware. Embedded firmware is a program which controls all the hardware which is present in the chip. So embedded firmware will be written by the programmer and it is dumped onto the chip before the manufacturing of embedded system. So it is a control algorithm or program instructions or the configuration settings that an embedded system developer dumps into the program memory of the embedded system. The embedded firmware can be developed in various methods like write a program in high level language like embedded C, C++ using an integrated development environment, that is IDE. The IDE will contain an editor, compiler, linker, debugger, simulator, etc. IDEs are available for different family of processors and controllers. Or writing the program in assembly language using instructions supported by your application's target processor or controller. So next other system component is reset circuit. The reset circuit is essential to ensure that the device is not operating at a voltage level where the device is not guaranteed to operate during system power on. The reset signal brings the internal registers and the different hardware systems of the processor or controller to a known state and starts the firmware execution from the reset vector. Okay, so these are the functions of a reset circuit. The first one is it is essential to ensure that the device is not operating at a voltage where the device is not guaranteed to operate during the system power on. And then the reset signal brings the internal registers and the different hardware systems of the processor or controller to a known state and starts the firmware. Firmware means the operating system of the embedded system execution from the reset vector. Okay. Now what is reset vector? We have studied enough about this in the first chapter of the syllabus, that is under ARM, right, when we discussed about basics of ARM Cortex M3 processor. So reset vector is the address of the interrupt service routine which occurs in response to the reset exception. So when the reset exception occurs, the interrupt service routine or the program which should execute in response to the reset exception will be executed, and the address of that, the starting address of this reset interrupt service routine will be placed at the very beginning, at the first location of the program memory, that is at 0000, whatever may be the number of bits per address. Okay, the first location, the 0th location of the program memory will be for the reset vector. So as soon as the processor is reset, reset vector is read, okay, that is placed into the program counter, and then The interrupt service routine, which is placed at that address which is present at 0th address in the program ROM, will be executed to reset the processor. Okay, so normally from the vector address 0x0000 for conventional processors or controllers. The reset vector can be relocated to any other address for processors or controllers supporting bootloader. Okay, in the processors or controllers where the bootloader is a program which is executed to load the operating system from hard disk into the memory. Okay, that will be stored, the bootloader program will be stored in the program memory. If that is the first program stored starting from the 0th location, then the reset vector will be relocated to some other address in the memory. Otherwise, by default, the reset vector will be the first location. Reset vector will be present in the very first location, that is in the 0th location of the program memory. The reset signal can be either active high, the processor undergoes reset when the reset pin of the processor is at logic high, or active low, that is the processor undergoes reset when the reset pin of the processor is at logic low. Now there are two circuits. First circuit is for the active high reset signal, and then the second circuit is for active low reset signal. Okay, so this is for the active high reset signal generation, where you can see the signal is taken from the point, okay, which is after the capacitor, and the other end of the capacitor is connected to VCC, and then by a resistor this point is connected to ground, and then the resistor is connected parallelly with the freewheeling diode. Even in the other circuit, the circuit which is used for active low reset pulse generation, where we have resistor connected to the VCC, and then at the other end of the VCC the active low reset signal is taken, which in turn again connected to the capacitor, and through capacitor to the ground. So here also resistor is connected parallel with the freewheeling diode. Now what is the role of the freewheeling diode? Freewheeling diode is used to protect the circuit from unusual damage caused due to abrupt reduction in the current flowing through the circuit. Okay, it protects the circuit from damage caused due to abrupt reduction in the current flowing through the circuit. So when this happens, that is when the abrupt reduction in the current flowing through the circuit happens, the freewheeling diode gets short circuited, and the voltage spike is thus short circuited across the coil. So the one more system component present in an embedded system is brownout protection circuit. Okay. The brownout protection circuit prevents the processor or controller from unexpected program execution behavior when the supply voltage to the processor or controller falls below a specified voltage. The processor behavior may not be predictable if the supply voltage falls below the recommended operating voltage. It may lead to situations like data corruption. A brownout protection circuit holds the processor or controller in a reset state when the operating voltage falls below the threshold until it rises above the threshold voltage. Certain processors controllers support built-in brownout protection circuit which monitors the supply voltage internally. If the processor controller doesn't integrate a built-in brownout protection circuit, the same can be implemented using external passive circuits or supervisor ICs. So the figure shows a brownout protection circuit which is used to prevent the system whenever the supply voltage goes below the required operating voltage of an embedded system. The other system component is oscillator unit. So oscillator unit is a very important part of an embedded system because the oscillator circuits generates clock signals which will act as a timing reference with respect to which all the operations of the processor or the controller take place. A microcontroller is a digital device made up of digital combinational and sequential circuits. The instruction execution of a microprocessor or controller occurs in synchronization with the clock signal. So all the operations, the program execution, instruction execution are synchronized with the clock signal, and with respect to this clock signal all the operations take place. So we define the time of execution of an instruction, right? Time taken by the processor to do something, to execute something, right? So everything is defined with respect to the clock signal, which is generated by the oscillator circuit. The oscillator unit of the embedded system is responsible for generating the precise clock for the processor. Certain processors controllers integrate a built-in oscillator unit and simply require an external ceramic resonator or quartz crystal for producing the necessary clock signals. Certain processors or controllers chips may not contain a built-in oscillator unit and require the clock pulses to be generated and supplied externally. So some of the processors or controllers have this oscillator circuit built in, but some of the microprocessors and controllers will have the pins to which this clock circuit can be connected externally. Quartz crystal oscillators are example for clock pulse generating devices. So figure shows a microcontroller, and in the microcontroller two pins of the microcontroller are connected to an external clock circuit. So the quartz crystal is used there. Okay, so this is a symbolic representation of a quartz crystal which is connected across two capacitors and then to the ground. So this is a clock circuit. So two pins of the microcontrollers are connected to this clock circuit. Quartz crystal is used. So this clock circuit is external to the microcontroller. It is not a part, or it is internal to the controller chip. Okay, so we have here the physical appearance, how the quartz crystal resonator looks like. Okay, a discrete component, a quartz crystal resonator. Okay, there are some crystal oscillators here. Okay, so here there is a microprocessor, and microprocessor is also connected to an external oscillator unit. So the clock circuit is oscillator unit itself is external to the microprocessor, whereas oscillator unit is internal but the clock circuit is external. Okay, there is a difference between microprocessor and microcontroller. Okay, oscillator unit is internal to the microcontroller. Okay, and it is off the chip or external to the microprocessor. This oscillator unit is in turn connected to the clock circuit. One more system component is real-time clock or RTC, the system component responsible for keeping the track of time. RTC holds information like current time in hour, minutes and seconds, in 12-hour or 24-hour format, date, month, year, day of the week, etc., and supplies timing reference to the system. Right, every system will have a real-time clock, right, which will supply the information in either 12-hour or 24-hour format with the date, month, year, day of the week, etc., right, with all the informations. So real-time clock is intended to function even in the absence of the power, right? It keeps on updating, right? Whenever we switch on, it doesn't start with the scratch. It doesn't start with day 1 or of the first day of the first month in the year, right? It goes on, so it works continuously. It will not be turned off even when the embedded system is not in a powered up position. So real-time clock is intended to function even in the absence of the power. Real-time clocks are available in the form of integrated circuits from different semiconductor manufacturers like Maxim, Dallas, Microelectronics, etc. The real-time clock chip contains a microchip for holding the time and data related information, and backup battery cell for functioning in the absence of power in a single IC package. Okay, so the real time clock is available in the form of a chip, right, along with the battery backup or battery cell integrated on a same silicon package. The real time clock chip is interfaced to the processor or controller of the embedded system. For operating system based embedded devices, a timing reference is essential for synchronizing the operations of the operating system kernel. The real-time clock can interrupt the operating system kernel by asserting the interrupt line of the processor or controller to which the real-time clock interrupt line is connected. The operating system kernel identifies the interrupt in terms of interrupt request number generated by an interrupt controller. One interrupt request signal can be assigned to the real-time clock interrupt, and the kernel can perform necessary operations like system date time updation, managing software timers, etc. when an real-time clock timer tick interrupt occurs. The one more system component of an embedded system is watchdog timer. Now, why watchdog timer is used? Usually, watchdog timer is used whenever there is a runtime error in the program execution. What happens is, whenever there is a runtime error, it will take some time for the system to reset. That is because the watchdog timer starts either up counting or down counting from the initial count, and as soon as it reaches 0 in case of down counting, uh, the system is reset. So this is the application of a watchdog timer. So whenever there is a system execution error, that is program execution error, it causes the system to hang, and after some time, uh, what happens is, as soon as the system is hanged, the watchdog timer starts down counting from the initial value, and as soon as the counting reaches to 0, the system is reset. So it is a timer unit for monitoring the firmware execution. Depending on the internal implementation, the watchdog timer increments or decrements a free running counter with each clock pulse and generates a reset signal to reset the processor if the count reaches 0 for a down counting watchdog, or the highest count value for an up counting watchdog. If the watchdog counter is in the enabled state, the firmware can write a 0 for up counting watchdog implementation to it before starting the execution of a piece of code, subroutine, or portion of the code which is susceptible to execution hang-up, and the watchdog will start counting. If the firmware execution doesn't complete due to malfunctioning within the time required by the watchdog to reach the maximum count, the counter will generate a reset pulse, and this will reset the processor. If the firmware execution completes before the expiration of the watchdog timer, the watchdog timer can be stopped from action. Most of the processors implement watchdog as a built-in component and provides status register to control the watchdog timer, like enabling and disabling watchdog functioning, and watchdog timer register for writing the counter value. If the processor or controller doesn't contain a built-in watchdog timer, the same can be implemented using the external watchdog timer IC. So you can see here the microcontroller or microprocessor is externally connected to a watchdog timer. Watchdog timer has a free running counter which will be loaded with the initial count. If it is up counting, it starts from 0. If it is down counting, it will start from the predefined counter value. And the output of the watchdog timer is connected to the reset pin because it causes resetting of the microprocessor or controller. And the request for the watchdog operation is sent by the microprocessor or controller whenever there is a runtime error in the firmware execution. Okay, as soon as the reset input is sent to the watchdog timer, it will start either up counting or down counting. As soon as it reaches the maximum count in case of up counting or reaches 0 in case of down counting, it will send a reset signal to the processor which will causes the reset. Okay, and both microprocessor and microcontroller uses the same system clock, so the timings of watchdog timer will match with the timing of the microprocessor or controller. Thank you. So this is the end of module 3. From the next lecture we will start with the module 4. So I request all of you to complete your reading of all these presentations of the module 3.